This video is about temperature and reaction rates. So what we observe in nature is that many chemical reactions, as you heat them up, they tend to go faster. We've actually observed this in lab. So if I were to do a plot of rate on the y-axis versus temperature on the x-axis, we would generally see, as indicated by the yellow curve here, that the rate increases as we increase the temperature. So I call this a typical case. So it actually makes sense why this would happen. We can explain it with a simple theory. So theories are explanations for what we observe in nature, and this is our observation that typically rates increase as you increase the temperature. So the way we can explain this is with a theory called collision theory. And collision theory that says that in order to react, the reacting species must collide. So that means they come together at the same place at the same time. They've got to bump into each other. Not only do they have to collide with enough kinetic energy. And finally, they have to collide in the correct orientation. So that means pointed the right direction towards each other. Let's look at a specific example to see how this works. So this is the reaction between H2 gas and I2 gas to produce hydrogen iodide gas. So in order for hydrogen iodide gas to be produced, the H2 molecules and the I2 molecules need to bump into each other. And when they do, we might imagine that this kind of process happens. So here's an H2 molecule, and it's flying this direction towards an I2 molecule that is flying towards it. So we're going to have a head-on collision. And so as they begin to collide, we begin to form a bond between this H and the top iodine, and form a bond between this H and this iodine. At the same time, we are breaking the bond between the two hydrogens and breaking the bond between the two iodines. So as this happens, these two molecules come together, the electron clouds are going to rearrange a little bit, and then these two molecules, after they bumped into each other, are going to fly apart as separated HI molecules. So you see they have to collide, they have to bump into each other. If they don't do it hard enough, the bonds may not break, or they might not get close enough for the new bonds to form, and they have to be oriented correctly. So if I had pointed the H, just one H to one I, then it might not have worked out correctly. So they have to be in the correct orientation. So how does collision theory then explain why increasing temperature increases the rate? Well, what we remember from the kinetic molecular theory is that temperature is proportional to the average kinetic energy. And we know that for a single particle, the kinetic energy from physics is 1/2 the mass of the particle times its speed or velocity v squared. So the faster a particle is moving, the higher its kinetic energy. So as we increase the temperature, we are increasing the average kinetic energy, which means we're increasing the typical speed at which these particles move. So if we increase the speed, we're going to do what? Well, we're going to increase the number of collisions because they're simply moving around faster, so they have a greater opportunity to bump into each other. Also, we've increased the chances that they bump into each other hard enough to do what they need to do to get the reaction to happen. And by colliding more often, because they're moving around faster, we provide more opportunities for them to collide in the correct orientation. So collision theory and knowing about the connection between temperature and kinetic energy offers an explanation for why we observe this trend. So if this was a typical case, you might ask, are there atypical cases? And yes, there are. Let's look at some of those atypical cases. So in this case, the rate starts out as we increase temperature, pretty much like we saw before, but then suddenly something crazy happens and the rate starts going super fast. So what's going on here is we might imagine that we have an exothermic reaction, and so as we start increasing the temperature, that reaction starts to happen more quickly, and so it produces more heat. Eventually we get to a point where it's producing heat so fast that we can't remove that heat fast enough, and the reaction simply gets hotter and hotter and hotter in the reaction center, and the rate accelerates out of control. We call that a thermal explosion. Exciting to see from a distance, but you don't want to be in charge of the chemical reaction when that happens. Another atypical case happens in this circumstance, where we might start heating up a reaction and it starts to increase, but then at some point it starts to decrease again. So it seems like it's going faster for a while, but then suddenly it starts to slow down. So this happens oftentimes in biological systems where chemical reactions are catalyzed by enzymes. And enzymes are proteins, and once you get a protein too hot, you begin to denature it or cook it. And once it's denatured, it tends not to function as well. So once we get the reaction too hot, we might see that the rate begins to slow down because we start destroying the enzymes, the catalysts that are responsible for catalyzing our reaction and making it go fast. So these are some atypical cases. But let's stick with the typical for now. So it might be very useful for us to avoid things like thermal explosions to be able to know how to predict the rate of a reaction as a function of temperature. So if you give me a particular temperature, I could tell you what the corresponding rate is going to be if I knew something like an equation for this curve. So that would be very useful. So if we go in and look at what we know about how to calculate rate, so rate is equal to a change in concentration of some compound. So let's imagine that A is a reactant. And so we're looking at how many moles per liter go away in a given unit of time. So that's how we determine rate. And we know how rate is controlled by concentration. That's given by a rate law, which is a specific rate constant times the concentration of each reactant raised to some power. So let's imagine that we just have two reactants, some substance A and some substance B. So remember, X and Y are called orders, and we call this a rate law. Rate laws explain mathematically how rate depends upon concentration. So these orders, these exponents, don't tend to depend on temperature. Concentration doesn't depend much on temperature. It changes a little bit just because the volume is changing if these are in moles per liter. So most of the temperature dependence then is hidden in this rate constant K. So it's funny that we call it a rate constant because it's actually not constant. We're proposing now that it must depend upon temperature. So if rates go faster at higher temperatures, it must be the case that K increases with increasing temperature. So it might look something like this, like the graph that we drew. So as we increase temperature, we're going to increase K. Bigger K means a faster rate, according to the rate law expression. So we'd like to know an equation for how K depends upon temperature. Well, a Swedish chemist by the name of Svante Arrhenius came up with this equation that bears his name. So this is the Arrhenius Equation. And this is an empirical equation. In other words, he didn't derive it from theory. Arrhenius looked at a whole bunch of different reactions and discovered that many of them fit this pattern. And so here's the Arrhenius equation. I might mention as an aside that Arrhenius is famous for lots of other things. He came up with a theory for acids and bases. He was also one of the first to propose that increasing the global carbon dioxide concentration might lead to a warming of the planet. So he was actually thinking about global warming way back in the 19th century. So this is the Arrhenius equation. K equals A, E raised to the power negative, then the quantity EA divided by RT. So let me define all these terms for you as we go through here. So capital A, so there are two important parameters in this equation, A and E sub A. So sometimes these are called the Arrhenius parameters. First parameter A goes by several different names, unfortunately. Sometimes it's called the Arrhenius prefactor or simply the pre-exponential factor because it is in front of this exponential function, E. Other times it's also called a frequency factor because it's related to how frequently molecules collide in effective collisions. So that's one of the important parameters. The other important parameter, E sub A, is called the activation energy. And we'll think a little bit about what that means here in a minute. Some of the other terms that you see in here, little e is just Euler's number. It's one of those rational numbers like pi that has a whole bunch of decimals that never repeat themselves. And its value is 2.7188281828 and blah, 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 46, dot, dot, dot. Anyway, so that's an example of Euler's number. So we're going to take Euler's number and we're going to raise it to this power, negative EA divided by RT. R is our friend, the universal gas constant. And for purposes of problems here, we're going to want that gas constant in SI units. And that value is 8.3145 joules per mole degree Kelvin. Then in the denominator, we also have, importantly, T. And this is what we were trying to get at, the connection between rate, given by the rate constant, and temperature, T. So T is just the Kelvin temperature. So that's the Arrhenius equation. And it turns out that these two parameters, A and EA, these Arrhenius parameters, they vary depending on what reaction you're talking about. So these are reaction dependent. But these are also properties that you can, in principle, go out and measure for a chemical reaction. And once you know them, then you can calculate what the value of K is at any temperature. We just have to plug everything into this equation. So how might you do that? How might you determine what the Arrhenius parameters are for any particular reaction that you're curious about? Well, it helps us a little bit if we rewrite the Arrhenius equation. So here's our Arrhenius equation again. And so what I'm going to do to rewrite this equation is I'm going to do a little bit of math on it. So I'm going to take the natural log of both sides of this equation. It's an equality, so I have to do it to both sides. So I have the log of K equals the natural log of AE to the minus EA over RT. So there's a property of logarithms that you might remember, that the natural log of A times B is equal to the natural log of A plus the natural log of B. So I'm going to use that to separate this A and then this exponential function. So over here I'm going to say that this equals the log of A, and then I have the log of E, Euler's number, to the minus EA over RT. Now you may also remember that the log function, the natural log function, and E, the exponential function, are inverse functions. So the log of E raised to the x power is just equal to x. So it sort of undoes that property. So I can rewrite this then as log A, then minus EA over RT. All right, so I got rid of the natural logarithm. This minus sign that's right here is the one that just got pulled down right there. Okay? So I'm going to rewrite this one last time. So we've got natural log of K over on the right-hand side equals natural log of A minus the quantity EA divided by R. So those are just constants. And then we have 1 over T. And in principle, temperature could vary. So if we look at this, we might recognize a particular mathematical form. So if we let this side, log K equal Y, and we let this thing, log of A is a constant, so this is just going to be a constant. Let's call it B. And then we've got minus EA over R, so I'm going to call that M. That's just another constant, negative EA divided by R. EA is a parameter, R is a universal constant, times 1 over T, and we're going to call 1 over Tx. Then you will immediately recognize that this has linear form. So this tells us that if we go out and we do some experiments where we measure K at several different temperatures, so you may have done some experiments in your laboratory, and we have done some experiments in our laboratory where we determined K, and that was at one particular temperature. So we would just have to do those experiments again at a different temperature, different than room temperature, several times, and then we could do a plot like this. We could plot on the y-axis log K, so we have several different K values. We could plot those. Versus on the x-axis, we would plot 1 over temperature. So let's scroll down a little bit more so give us some more room. So we would plot 1 over temperature, inverse temperature. And what you would see is that we would get a straight line. The straight line would have an intercept up here. The intercept with that axis would be the natural log of A. So if we know what that intercept is, then we could compute what the Arrhenius prefactor is. And then the slope of this line would be equal to negative EA over R. So if we know the slope of this line, we could then determine what the activation energy is from that slope. There's another way of writing the Arrhenius equation that's also sometimes helpful, so I'm going to go ahead and write that down for you guys. And this version of the Arrhenius equation is useful when you know K at one temperature, and you need to find the value of the rate constant at some other temperature. So here's a variation of the Arrhenius equation that would do that for you. So it says the negative log of K2 divided by K1. And so these are the rate constants at two different temperatures, temperature 1 and temperature 2. And that is equal to negative EA over R. So in order to use this equation, you already have to know what the activation energy is. So you already have to have done these experiments that I was talking about to determine that Arrhenius parameter. It's going to be 1 over T2 minus 1 over T1. So this looks a little bit like the Clausius-Clapeyron equation for vapor pressure. It has a similar form, so you may have recognized this mathematical form for the equation before. So if you know any, so there are 5 variables on here. Let's circle them. 1, 2, 3, 4, 5. So if you know any 4 of these variables, then you can use algebra to solve for the 5th. And this is most commonly used when you know activation energy and you know the value of the rate constant at one temperature, T1, and you want to find the value of the rate constant, K2, at some other temperature, T2. So that's how you might use this equation. So let's think a little bit about what activation energy means. So activation energy is really just a parameter, but one way that people interpret activation energy is as the minimum amount of energy that you have to put in for a reaction to sort of get started. So that might be a little definition of kind of what activation energy, EA, is about, or it's a way of thinking about it. I mean, here's a model. Let's think about this situation. So we've got a great big giant boulder, and it's up here high on a cliff. And we know that we could lower the gravitational potential energy of that boulder by dropping it down so that it's over here at this lower position on the ground. But in order to get that boulder over here to lower its energy, we first have to push that boulder, which is a lot of work, up the hill to this top point, and then it can roll down by itself from there. So we have to put in some energy to get things going. You can think of that as the activation energy to get this boulder to lower its energy by falling down to a lower position, right? So if we just drop the boulder, it would lower its energy. So that would be the activation energy that we would have to put in to get this to happen. Well, chemical reactions are very similar. So we can do another kind of plot that's kind of like this graph that I just drew, and we plot energy on this axis, and over here we plot kind of a funny variable that we're just going to call reaction. RxN is my abbreviation for reaction progress. So it measures how closely we're moving from the arrangement of atoms that looks like the reactants to the arrangement of atoms that looks like the products. So over here are our reactants H2 and I2. Then as those guys come together and their atoms get close in the correct orientation, they form that complex that we drew a little bit earlier, where a bond is beginning to form between an H and an I at the same time that the bond between the two H's is breaking, and at the same time that a bond between the H and the other I is forming, and that bond between the I is forming. So this elementary step of a mechanism involves the breaking of 2 bonds and the making of 2 bonds simultaneously. Now it has to happen in a well-organized event, carefully orchestrated like a symphony orchestra. In fact, this kind of reaction is called a concerted reaction. Kind of like a concert. Everything has to happen at exactly the right time. So this structure right here, this particular arrangement of atoms, it turns out has a high energy. And so the distance between where we started and this higher energy position, that's often interpreted as the activation energy. So that's the barrier to this reaction. So this arrangement of atoms here, this high energy arrangement of atoms, is sometimes called the activated complex. So that's activated complex. So it's activated so that it can either go back this way and undo itself to remake the reactants, or it can move forward and form the products. So the products over here would be the 2 HI molecules. And they would be at lower energy. So this difference in energy here between this dashed line and this dashed line, that would be the energy change for our reaction. So that would be close to the delta H for this reaction. And this extra bit would be the activation energy for this reaction proceeding in the forward direction. So we might even put a little comma next to our A and write FWD for forward to remind us that that's the activation energy for this reaction when it goes in the forward direction. And the energy at the very top of this hill, that would be the energy of this activated complex. So this particular arrangement of atoms is sort of a high energy arrangement, and that would be the activation energy. So we have to put in at least that much energy in order for this reaction to go. So that's why activation energy is often interpreted as the minimum amount of energy.